Welcome to the Spectroscopy and Coherent Scattering Instrument, the SCS. At the SCS instrument, we are looking at the electronic properties and quantum phenomena in complex materials and nanostructures. And we work in the soft X-ray range, which allows us to utilize special absorption resonances in the material, which gives us a specific state and element-specific insight into these materials. The emphasis is actually to look at the states in these materials and how they evolve in time. And we use optical stimulus, for instance, to drive them into a new state. And we follow then the transient in space and time. Following this, understanding these transients allows us to better understand the processes in these materials and may then allow to engineer new materials and devices in applied science. I'm sitting here in the experiment hatch of the SCS instrument, and from here it's another 415 meter upstream to the source point of our instrument. In the tunnel towards our experiment hatch, we have a soft X-ray monochromator that allows us to monochromatize the beam that we further then bring into our experiment hatch. And in our experiment hatch, we have here inside the last 15 meters of our instrument. And in the first part, we actually first have an intensity monitor that allows us to normalize our detector signals to the incoming radiation. After the intensity monitor, we have the refocusing optics, which allows us to focus the incoming radiation down to a micron. This focus is actually variable, so we can have a tight focus or we can also enlarge the focus, and thereby we can change between different operation modes. We can do very high peak intensity shots, single shots, destructive shots on materials, but we can also enlarge the beam such that we do not leave radiation damage to the sample, which is a rather spectroscopy-like mode that you can drive in a pump probe fashion in solid states. So right behind me, you can see the experiment station. That's basically the heart of the instrument, where we where we can apply a magnetic field to the sample. And just right in front of the experiment station, we have the laser encoupling, which allows us to bring the optical laser to the sample and overlap it there in space and time with the X-rays. Then from the interaction point, we record downstream outcoming radiation. We work usually in a transmission or scattering mode with this current setup. And we record either small angle X-ray scattering or coherent diffractive speckle patterns, so to speak, that allows us later to, for instance, do image reconstruction from the small area that we illuminated. At the very end, we have then coming to the detectors that collects the scattering from the sample. And this is a very special detector because it allows a very high frame rate. We can record up to 8,000 frames per second with this detector. And but this is not only the last point of our instrument. Actually, this detector has a hole in the center that allows the direct beam to go through the detector. And this finally impinges on another detector that just records the transmitted intensity. And with this, for instance, we can do absorption spectroscopy and look at this at the same time like as a scattering. In the upcoming winter shutdown, we will actually extend the capabilities of our instrument. We will add as a new tool inelastic X-ray scattering, which allows to look at the low energy excitations in materials. For this, we will bring actually 2 more instations to the interaction point behind me, and we will have a high resolution spectrometer to resolve these low energy excitations.